partial least squares is not the most popular model out there, but it has its place. And because its place is here, we might as well stop and introduce it along the way. So PCA is unsupervised. When we're drawing those directions and maximal variance, they don't take into account any target or response variable y. PLS, partial least squares, is a supervised alternative to PCA. In this method, the directions are drawn to not only best summarize the X data, but also to best predict a target or response variable y. So I like students to have this kind of in their toolbox under the label, a supervised version of PCA. Now, you don't have to understand all the mathematical details. Indeed, most of them are kind of beyond what we talk about. But when we draw that first PLS direction, call it Z1, again, it's a linear combination of predictor variables. And here, the coefficient of each predictor variable, of the jth predictor variable, is just the simple linear regression coefficient of y on xj. So this means that the highest weight is given to variables that are most correlated with y. I should add, of course, that this is all on standardized data, so having a larger regression coefficient necessarily means it's more correlated with y. After we've drawn that first direction, the data is orthogonalized. That means it's projected onto the subspace orthogonal to the first component. And in that subspace, the next direction is drawn in the same manner. And we just repeat until we have P components. This is popular in some scientific disciplines, particularly when we have more than one target or response variable. But in practice, it doesn't tend to perform better than PCR or ridge regression or lasso regression, which we'll talk about in Fall 3. I'm going to show you an example of this using the big data problem that was introduced in the last optional video. And to implement PLS, we don't have to change much. In fact, the only thing we have to change is this method to PLS. And again, I'm doing twofold cross-validation to determine the number of components. I'm only putting in the training data to this operation. And again, I have to admit, I didn't even run this cross-validation procedure because I know that it's going to output the maximum number of factors, which is 15. So I skipped this step because it's going to take a little while. And I went straight to proc PLS. And I have to do that same ODS output trick in order to get the parameter estimates to put into proc score. And again, if you compare that PLS estimates table from that we just output, if you compare it to work.ols, which is estimates output from proc reg, you'll see that they have the same information, but in a different format. So these two procedures here just transform PLS estimates to match the structure of work.ols. And then we can use proc score. Using those scoring coefficients, I am using the output from the second proc core that we've done in the code, which contains the original data, original test data, plus the OLS predicted values and the PCR predicted values. So now I have all of the data and I'll have all three predictions on the same table. I'm going to call that final table out 3. And finally, I can compare the 3 models, and I can do that in a few ways. First, using R squared. Admittedly, it's just R. I haven't squared it yet, but bigger is better, and PCR is still the biggest. PLS does beat OLS, but not by much. And it actually has a larger error than OLS when we look at root mean squared error on the test data. So interestingly enough, it's got a better R squared, but a higher root mean squared error. So really nothing definitive there except that, you know, PCR is still the winner.